I would say the core development we are having here is a fully automated sensor-based sorting device. Yeah, so we are planning to combine laser-induced breakdown spectroscopy with hyperspectral imaging, also with artificial intelligence software in the back, and all of that will then be combined in this fully automated sorting. Yeah, so that will be the main aim here, to create new qualities of materials, and whenever we create new quality of sorted materials, this will usually also leave over some other residues where we might not have a full application or the best valorized application today. And that's actually what brings us to this topic today. And at this point, I would like to hand over to Ananda now. He will introduce further the materials and the project setup here. Thank you.
Yeah, so this is the resource partners. Thank you for your wonderful introduction, by the way, Alex, much appreciated. And this is the resource partners. We are a team, and some of these resource partners are also there in this workshop, I believe. And from CPI, we are mainly present in two work packages. The work package 2, which is life cycle assessment and techno-economic analysis. I believe once we go forward with the other next few slides, then it will be more apparent why this is kind of a very highest consideration. But I am representing today from work package 9.2. Work package 9.2 is a big team where we are exploring areas which is beyond refractory. So we are, selecting the material, as Alex pointed out in the earlier slides, which have a most challenging to recycle. That 30% or so fraction of 0 to 5 millimeter, and we are trying to incorporate it into suitable polymer matrix, and we are exploring new areas of application, whether this can be effectively utilized into value-added application purpose. Now, next few slides, our colleagues will be talking a little more details on that. But just to clarify, we will be mostly talking about two materials here. One is a steel industry-based 0 to 5 millimeter size fraction. We will henceforth call it as a ref ferro. And the cement industry one, we will be calling it as a ref chem. So in the next few slides, one of my colleague, Jack, will be talking about the characterization part. We need to understand this material first quite well in order to incorporate it and to find suitable application area. And then we will highlight some of these examples of some of these application areas that we have worked with. So without wasting any time, I'm just handing over to Jack to talk about the characterization or talk about more of these materials.
Thanks, Ananda. So as Ananda mentioned, these are spent materials. So we decided that to figure out how we were going to be able to use these materials and what we might need to do to use these materials. We began a characterization study. So we first looked at the chemical composition of these spent materials. And broadly, we can see that they're comparable to what we might expect that's used within the bricks. So for instance, we see a lot of magnesium oxide in there and calcium species like calcium carbonate. We see these across a range of different characterization techniques. So the XRD, FTIR, EDX, and the Raman. And we also see some potential impurities which have been added through processes that these materials have gone through. So for instance, we can see potassium within the material from the cement industry, which is potentially added in the cement production process. We also looked at the particle size distribution of these two materials. So we received two materials that were pre-sorted to below 5 millimeters. And within this size fraction, we then see bimodal distributions. So we see materials, we see distributions centered around 200 micrometers and 1700 micrometers. And we also looked at the bulk and skeletal densities of these materials. So the skeletal density here is taken into account pores and voids when it calculates the density. We see then from skeletal density that these are reasonably high density materials, both above 3 grams per centimetre cubed. We also had a look at the physical properties of these materials. So having a look at the electrical resistivity, the dielectrical permittivity, and the magnetic permeability. Whilst we don't see anything that's particularly of interest to us in the magnetic properties, we do see quite interesting properties, the electrical and dielectric properties, and we see a difference between the two materials. So for the cement industry material, we see a reasonably high electrical resistivity and a reasonably high dielectric permittivity in this material. Whilst for the ferro material, we see it's a reasonable conductor. And again, in the dielectric permittivity, we see that it's an inductor. So, for instance, with the Refractory material, this conductivity is on a kind of par with carbon black. So that's an area that we could potentially look to use this material in, placing things like carbon black. So just to summarize there, we have had a look at the characterization of these two materials. We see that they're both bimodal particle size distributions, and their interesting properties really are in the dielectric and electric properties. And we see that we can potentially use the RefChem material for electrically resistive applications, whilst the Refractory material we can potentially use for electrical conductive applications. Both these materials are also thermal insulators, as we would expect, and so they can potentially be used for thermal resistivity applications as well. So as these materials have a bimodal size distribution up to 5 millimeters, for certain applications, we realize that we need to do some processing of these materials to put them into applications. So for instance, to put into a polymer system, we need to process these materials down to a size class with a D50 below 10 micrometers. So we process these materials by milling. We first began in the lab on a benchtop scale with about 10 grams of material, using a planetary ball mill to reduce this to below 10 micrometers in size. We're using an adaptive DOE software to guide our optimization of this process. And then we upscaled this to a multi-kilogram size process, milling this material. And we can see that we changed this material. So we reduced the D50 to below 10 micrometers. The D90 is also below 10 micrometers. We reduced the skeletal density and the bulk density slightly. So the bulk density is just explained by there being more voids when we reduce the size of this material, which is expected. And the skeletal density is due to us changing some of the magnesium oxide to magnesium hydroxide, which has a lower density. And we also see this in the compositional changes. So when we look at the XRD, we can see that we've created some magnesium hydroxide from the magnesium oxide. We also performed some leach testing on these materials to see if there's any mobile ions present. We can see that there are some mobile ions, and these can be explained by the processes that these materials have gone through. So for instance, with the MRFM material, we see the potassium and the chlorine that can be expected from the cement production industry. So I'll pass over to my colleague Dan now, who will talk about a material passport that we've created to help us identify potential use cases for these materials.
Thank you, Jack. So as Jack mentioned now, we did then create all of the results from the analysis that we've done of this milled material, this size reduced material, and put it into a material passport for both of the materials. So this is some of the information present there. So we have some information about colour. That is the colour of the batch that we received. Obviously, with being a waste material, there's still analysis need to be done to see how reproducible that colour is. Also, you can see there the main changes from the magnesium oxide to hydroxide. And so like residual moisture content. So these materials pick up a slight piece of moisture, slight amount of moisture on sitting, about 0.35% on sitting. and at 1,000 degrees Celsius on TJ, they lose about 15% of the mass from different compounds. So the loss of water from the magnesium hydroxide into the magnesium oxide again, and loss of carbon dioxide from the calcium carbonates. So that is the MREF SEM. We also have the same data for the MREF ferro with similar results, a little bit larger loss in TJ because there is more carbon in the form of graphite in the formulation, which comes off at the higher temperatures. And again, this color is different. It's a darker gray because of that graphite content, but we still need to confirm how reproducible that color is if you're looking at a coating application. From this size reduced, we can also surface modify these materials. So we can use compounds like silanes to treat the surface, to change the surface energies, which allows tailoring of the surface energy of the material to incorporate better into different polymer systems. For example, you can use this glymo to incorporate better into epoxies, or an aptez into a polyurethane. And on the right there, you can see the graph where we've looked at different concentrations of the glymo on the sample itself. You can see as you load that up, you get diminishing returns of the decrease in the surface energy. So what we can do is when we're doing applications, we can test to see whether we can put the material in as it is, or whether if we surface modify it, do we get better applications or better properties from the application. And on that note, I'll now move into some application usages that we've tested at CPI. So these are just like the starting evaluations of different applications to see how they would fit in. We are going to show some key findings here. It's not exhaustive data and not an exhaustive list of the application areas that we have tried or what could be examined. So the first one is a burning test for suitability used in building and infrastructure related applications, like adding the outside of the buildings. We did this within with the help of the University of Edinburgh, who did the burning test. This came from where Jack mentioned before that these have quite a low thermal conductivity. So we're looking to see how it would help in that application. So I can see there is on the left-hand side, we have the setup that was used at Edinburgh, where they heat the sample up until it ignites. So on the right-hand side there, we've got the graphs of the raw epoxy, epoxy with aluminium trihydrate, which is the commonly used filler for flame retardant coatings, and then along with our MREF SEM and MREF ferro materials. So you can see there is we do get slight increase in the time to ignition compared to the raw epoxy with our materials, but it isn't as good as the industry standard aluminium trihydrate. These are all initial look tests. These are on the full sweep of what's possible. But what you can then see is if you actually look at other data points in there, so for the heat released, so you can see because of the thermal insulating properties here, we don't get as high of a spike of heat release, but we get that over a prolonged period of time. So we're elongating the burn effectively. And you can see that the same is seen in the carbon monoxide concentrations, where the actual peak of the data is lower, but we've broadened out that release. So we're not suggesting that we fully replace aluminium trihydrate with instant materials, but these materials could be of interest to mix with aluminium trihydrate to improve already good thermal properties of materials by extending that release. Another test we looked at was, could we use it as a mechanical enhancement for thermoplastic composites? So For this test, we extruded it in polypropylene at 28%. You would usually use calcium carbonate as a filler in this instance. So looking at how the MRF and MRF ferro affected those results. As you can see there in the left-hand graph, we get about a 20 to 45% increase in the tensile modulus of the material. So it's making it stronger before it breaks. But on the next graph in, you can see that the actual strain to break is reduced, so they're becoming a bit more brittle in their application. So there is an improvement. There's also a little bit of a drawback there. In this, before I mentioned that we can coat these with silanes to surface modify them. So we modified this with a silane specifically for polypropylene, which is the right-hand graph there. And what you can see there is the coating with the silane in this instance didn't give us large benefits to the modulus in this case. So for this application itself, you would not need to coat the particles. You could just use them as the milled material itself. Another application we look at was coatings, performance coatings. So we've started exploratory protective coatings using an alkyd resin system. So what you can see there on the left is the coverage that is possible with just 2 coats of this, the MRF ferro material on a sheet of steel. So we can get good coverage and a nice base layer. We've got some ongoing investigations in the mechanical properties, looking to see abrasion resistance, wear resistance of the coating. Can we make a tough coating out of this to protect the steel? We're also looking at potentiostatic EIS, looking at the coating integrity to whether it could be used as an anti-corrosive coating or not, or whether it would just be a decorative base coating made with recycled materials. Another application that we were looking at was the use of dielectric ink within printed electronic devices. So these are cheap electronic devices that are mass market, they're not high value in of themselves. And this was in collaboration with another Horizon 2020 project in Sustainaprint. We have the link to their website there if you want to have a look at that. But what we're doing is we're looking to replace the dielectric ink in an electronic device. So this is an ink that you use to coat over an electronic track, so you can then print over the top and you don't get interference between the 2 tracks themselves. Example of that is the top middle there. So what we're looking at was could we replace the barium titanate with our material, in this case the MRF chem, because that was the most dielectric of the 2 materials. And what we found was we could mix this in. It could give us good dielectric properties, but the actual dispersion itself was poor and the adhesion was poor, which was the same for the actual reference of the barium titanate. But in this case, when we surface modify this material, we can then improve the adhesion to a much greater degree, and it actually doesn't delaminate and flake off like the previous formulations, and we get the good dispersion and we maintain the dielectric properties. So this was a very good win for the Sustainaprint project because they could use up to 98% recycled materials in their final product, which was the main target of their project. So yeah, I've just gone through a few examples of the applications that we've been looking at. I've got to say thanks to Edinburgh University for the processing and the combustion testing of the epoxy samples, and Pillamec for doing the large-scale milling to give us enough material to do all the testing that we've done. And then just a few of the people that we've done some work with and partnered with in Sustainaprint in the example I've just shown, but also Zentia and Paltech, who are both looking into this material as possible recycled filler materials for their current products, future products. So, got the QR code there. That will, if you would like to scan that, that will take you to the ReSoURCE project website. It will also take you to the data sheets for the different materials. For the MRF SEM and the MRF Ferro materials will both be linked in there.
If you want to discuss anything, discuss projects, more understanding more of our capabilities, how can we be associated with you and be a partner with you in your projects or in your product or in your process, please let us know. These contacts will be open, and we welcome any kind of a question or any kind of queries that you may have.